Hello everyone and welcome to our booth of Bauhaus Luftfahrt at ILA. Also welcome to everybody who is joining us through the live stream. My name is Katrin Ebner and I'm the Strategic Research Coordinator Hydrogen Aviation at Bauhaus Luftfahrt. I share this role with my colleague Dr. Arne Seitz, who unfortunately couldn't join us today, but I'll definitely try my best to represent him as well. So let's talk about pathways towards hydrogen aviation. So first of all, why would we even need hydrogen in aviation? Well, as we all know, aviation has set quite ambitious climate targets and we need to replace fossil energy carriers. So green hydrogen in that context is a scalable option and it also burns relatively clean, meaning we have no carbon-based emissions and we have also the potential to lower high altitude climate impact. As you can see here in one of our scenarios that you could also check out here at the booth, hydrogen has the potential to make a significant impact on emission reduction of aviation, here marked in green. So how do we get our hydrogen? Well, basically for hydrogen to be effective in emission reduction, we need to produce it from renewable energies. Consequently, there are some favorable locations to produce it. On the top, you can see favorite wind locations, right below favorite solar locations. As you can see, not only aviation or the transport sector would have an interest or could also have the potential to employ renewable hydrogen, but of course also other industries and other sectors have a potential of emission reduction by employing hydrogen. So we have a potential of synergies with these sectors. What is pretty special though about aviation is that we are aiming to employ liquid hydrogen. Why? Because we require high energy density. So basically, we also need to incorporate a liquefaction step in this production chain, which additionally consumes electricity. Due to a shorter production pathway though, producing liquid hydrogen still typically has advantage in production efficiency on the place of production as compared to, for example, synthetic kerosene via the PTL process, as you can see on the bottom right. So now, as we have our hydrogen, how do we use it in aviation? Well, actually, while it sounds pretty simple, this question is quite complex, as we try to illustrate here on the right-hand side, as it has many aspects. So first of all, liquid hydrogen as an aviation fuel has drastically different properties than kerosene. So first of all, it's a cryogenic liquid, of course, and also it is handled differently for that reason. As I mentioned before, it has quite different energy density, actually lower than kerosene when it comes to volumetric performance, which also needs to be considered aboard the aircraft. So this is not only relevant when we are talking in the context of production and logistics, but of course also relevant when we talk about aeronautic application. So to these two topics, so logistics of liquid hydrogen and also application aboard the aircraft, we will go a bit into more detail now. What is important for me to tell you though is that we have to consider all of these different aspects of hydrogen aviation in the context of a broader system transition towards hydrogen. So for basically having a holistic view on all of these different topics as illustrated here, our team at Bauhaus Luftfahrt brings in a lot of expertise as it's very interdisciplinary and can look at these questions from different angles. So as I mentioned, let's first take a brief look at liquid hydrogen logistics. So as typically there is rather cheap electricity available wherever we have a favorable production location of hydrogen, there may be also an advantage of liquefying it there. And that's why we mostly consider transporting directly liquid hydrogen. So of course we need to look at means of transport and also how to optimize different logistic chains, as there is a number of options as illustrated here. When it comes to means of transport, again, we have a number of options such as liquid hydrogen ship transport, via train, via trucks, etc., etc. And all of these are actually somehow technically feasible as illustrated here in these 50 shades of green. However, they differ significantly when it comes to their different properties, and oftentimes we have to consider the trade-offs. So to consider or to figure out the optimum transportation scenario, we have to consider, for example, location of the airport and also amounts of hydrogen needed there. Again, as I mentioned, both the electrolysis step and also the liquefaction step take a significant amount of electrical energy. So most cases that we looked at, it's favorable to actually liquefy wherever you produce and then transport the liquefied hydrogen. So now we have the liquid hydrogen at the airport, but what do we do with it? Well, actually, of course, we need to now store this cryogenic liquid, and we also need to distribute it at the airport and then fuel the aircraft with it. And there is actually a number of considerations that goes into that. When it comes to the fuel, for example, storage, handling, distribution equipment, technological development of all of the equipment involved, but also when it comes to the movements and also the fleet development and aircraft development. So when do we need what amount of hydrogen where, basically? So logically, as it's a cryogenic liquid, all of the handling equipment differs fundamentally. And all of this complex interplay, as here illustrated on the right-hand side of the slide, is actually tackled at Bauhaus Luftfahrt by simulations and modeling to understand what is the impact at airports of hydrogen introduction. So now, basically, we arrive at the question, we have this liquid hydrogen in the airport, but how do we use it in the airport? So basically, using hydrogen opens up different options of propulsion. We can rely on combustion-based technologies like gas turbines, other revolutionary heat engines, and we can also employ electrochemical conversion like fuel cells. To really, let's say, have optimum performance, sometimes, and maybe oftentimes, considering really the best synergistic combination of both can be very effective, as illustrated on the bottom. So now, basically, to use these different propulsion concepts and our liquid hydrogen on board, at Bauhaus Luftfahrt, we used our different expertise, put together our heads, and came up with different concepts for every segment that basically, with the main target in mind, basically, how can we overcome these intrinsic, let's say, disadvantages of hydrogen, as I mentioned, with the large, smaller energy density, also being a cryogenic liquid, etc., by using synergistic combinations of futuristic technology and advanced technology options. So what you can see here at first is the original concept that came out of it. It relies on propulsion of a high-temperature PEFC, polymer electrolyte fuel cell. And basically, in its dry wing, you can also use the space differently, let's say, than in a conventional aircraft and store subsystems. We can also use the surfaces of the aircraft to get rid of the waste heat of the fuel cell, etc. And in an initial assessment of the performance of the aircraft, we can see on the bottom right that actually, when we look at the block energy use at the design mission, it is on par with an aircraft that considers evolutionary development until the year 2035. And, spoiler alert, actually you will see this behavior for every segment. It's not only on par for some of these aircraft, it's actually even better. So let's look at the SMR. In this case, as described before, we actually rely on a synergistic combination of fuel cells and combustion by using a single gas turbine solid oxide fuel cell hybrid. Here the power share is 50-50 considered. And as you can see again below, not only is the performance of this initial assessment actually on par, when we also reduce the speed, we can actually have a better performance when it comes to block energy. And lastly, let's take a look at the long-range concept the team at Bauhaus Luftfahrt came up with. Basically employs, again, this hybrid concept, but in a different power share. So we have 1/3 fuel cell, solid oxide fuel cell, and 2/3 in revolutionary core engines. And also, as you can see here, it has a fuselage fan that basically makes use of boundary layer ingestion to have efficient propulsion. And again, the same motto, we can actually not only overcome the challenges of having liquid hydrogen on board. Initial assessments showed that the design block energy can actually be reduced. So, and that was a very brief look at our work here at Bauhaus Luftfahrt. As a conclusion, I want to again point out that, of course, hydrogen has very different properties from kerosene, and therefore brings a lot of new challenges to aviation, but it also brings new chances when it comes to emission reduction and synergistic technology use. And with that, I want to thank you for your attention, and I hope you stop by for many questions and discussions with me and my colleagues, and also, of course, I'd be happy to take your questions now. Thank you very much. Thank you. Again, questions, of course, can also be posed later.